Here's a short qualitative lecture and some demonstration involving yo-yos. Let's say that you allow a yo-yo to move downwards and it unfurls the string as it does. The string does so without slipping. Okay, if it does so without slipping, there is a torque that is exerted upon the yo-yo due to the tension in the string. This then ultimately causes the yo-yo to rotate as it moves downwards. As it moves downwards, of course, it will gain kinetic energy as it falls, and it loses potential energy. Some of that potential energy ends up being rotational kinetic energy. This then ultimately means that the yo-yo gains angular momentum as it unfurls the string. Basically, the situation looks something like this. Okay, so the yo-yo moves downwards. Yeah, I'll just go ahead and draw the yo-yo like so. And right here usually is where the axle is associated with the yo-yo, and then you have the string, for example, like this. Okay, initially there's going to be a tension vector like so associated with the string. Right here is gravity, force of gravity is downwards. Okay, initially as the yo-yo moves downwards, of course, it accelerates downwards. Okay, as it accelerates downwards, the string then unfurls without slipping. This then means that the yo-yo begins to rotate in this manner like so. This then gives us an angular momentum vector that is out of the board. Okay, so there's a rotation, like so. And then right here, I'll go ahead and draw an angular momentum vector out of the board, like so. Of course, the yo-yo gains rotational kinetic energy as it moves downwards, as potential energy is converted into kinetic energy. Okay, now let's say that the yo-yo reaches the bottom of the string, and the string can no longer unfurl. So because the string can no longer unfurl, this then means that static friction between the string and the yo-yo's axle, right here at this point, for example, is exceeded. This then means the string slips. So as the string slips, the yo-yo, however, keeps rotating, and the reason for that, of course, is because it has angular momentum when it reaches the bottom of the string. So that situation then looks like this. Okay, so now let's say that the yo-yo reaches the bottom. Okay, here's the yo-yo once again, and then here's its axle, like so. In this case, because the string has slipped, now picture the string as looking something like this. So then therefore you have a tension upwards, and then you have the force of gravity, mg, downwards, like so. And those two forces then cancel each other out because the yo-yo is just sitting down there at the bottom. The whole time that this is happening, however, because the yo-yo has angular momentum, it continues to rotate in this manner. So once again, using right-hand rule, here's an angular momentum vector out of the board like so. There's kinetic friction, however, between the string and the axle. This then slowly causes some of the energy to be lost as heat. Eventually, the string will catch once again, and then once the string catches, this then means that the string furls once again. In order for this to happen, however, the yo-yo has to move upwards. That then looks like this. Okay, so now the yo-yo moves upwards. Okay, now notice how I'm going to draw this. Once again, here's the yo-yo. Here's its axle, but now the string is in this direction, like so. Therefore, you have a tension upwards, and you have the force of gravity downwards, like so. The yo-yo, however, is continuing to rotate in this manner. Recall its angular momentum. So the rotation looks like this. Therefore, the angular momentum is out of the board, like so. And then therefore, as the yo-yo rotates like so, it has to furl upwards. As it furls upwards, then it slows down as it does, of course, and that's because the kinetic energy is being converted back into potential energy. In order for this to occur, however, in most yo-yos, what you have to do, of course, is you have to jerk the string upwards. In order to do that, this then allows you to add a little bit of extra energy to the situation, and then ultimately the string furls up as the yo-yo moves upwards once again. This then increases the tension vector from where it was before, such that initially at least the yo-yo begins to accelerate upwards in this direction. But that acceleration, however, decreases very rapidly, and then ultimately then the yo-yo loses energy due to heat, and also as it moves upwards, that kinetic energy converts back into potential energy. So the situation then basically looks something like this, once again just qualitatively describing all of this. So here's a typical yo-yo. Let me go ahead and tilt my phone. Like so. And now let me go ahead and manipulate the yo-yo here a couple of times. When you play with a yo-yo, undoubtedly, for example, you've usually done something like this. You've thrown the yo-yo downwards, like so. When you throw the yo-yo downwards, you then give it some extra kinetic energy as it rotates, and then therefore some extra angular momentum, ultimately when it reaches the bottom. Notice that I jerk the string upwards in order to have the yo-yo rise upwards once it does reach the bottom, for example, like so. If the friction, however, between the string and the yo-yo is enough, then the angular momentum of the yo-yo is actually enough for it to begin to furl the string back upwards once again without me necessarily jerking on the string. So let's see if that works. This typically works with newer yo-yos because you still have a lot of static friction between the string and the yo-yo's axle. For example, say something like so. So it was able to move upwards a little bit without me necessarily jerking it upwards, at least to a large degree. However, when you typically manipulate a yo-yo, you usually jerk it back upwards, for example, say, like so, as I'm doing here. Okay, a couple of other things that are interesting to note about yo-yos. Let me tilt the phone back to show you. Okay. Okay, let me erase this. And now let me use this yo-yo here for this demonstration, this red one. What I'm going to do is I'm going to position it like so, such that the string is here at the top of the axle. Okay, let me go ahead and furl it back up again some. Like so. Okay, and now I'm going to place it here flat on the desk, and then with this hand, I'm going to exert some tension on the yo-yo, such that ultimately it then accelerates. Okay, in which direction here on my desk is the yo-yo going to accelerate? Watch this. It accelerates to the right-hand side, and if you were watching carefully, you should have seen that the string actually unfurls. The length of the string that I'm having here in my hand gets longer, for example, like so, as time goes on. The reason for that, just in terms of basic kinematics, is as follows. Okay, so let me go ahead and draw the yo-yo like so once again. Let's say right here is the desk. Okay, right here we'll say is the axle, like so. And then let's compare, for example, the speed of the yo-yo relative to the desk at this point, and the speed of the yo-yo relative to the desk at this point here. Okay, let me assign some distances here on this diagram for simplicity. Let's call this right here our instantaneous axis of rotation, if you recall the basic kinematics of a rolling object. Let's call this distance here D. Let's call this distance here D. Let's call this distance here D, like so. And then let's say, for example, the speed of the yo-yo right here at the center is some speed V in this direction. Well, recall that if we think of this as the instantaneous axis of rotation, then as we rotate about that point, the angular velocity of all points of the yo-yo is the same. Therefore, the linear speeds have to be different at different distances from the instantaneous axis of rotation. So if I call this speed right here at the center V, then this speed here at the top, let's just call it V prime, for example, like so, is greater than the speed V. And the reason for that is because this distance here is greater than this distance here. So then therefore the string, as you can see, unfurls once again when I do say something like this. Like so. Okay, now watch this. Now I'm going to take the yo-yo and flip it over. Okay, let me furl it back up again like so. And I'm once again going to exert a tension on it here with my left hand off to the right-hand side. In which direction is the yo-yo going to accelerate? It's still going to accelerate to the right because I'm exerting a tension force vector to the right-hand side. But now watch what happens to the string when I do this. Notice that the string furls back up again. And the reason for that is because the speed of this point here where the string is, where I'm holding it, that speed there, call it V double prime, that's then less than this speed here. So V double prime is less than the speed at the middle, and then therefore the string furls up when I pull it in that manner. If you have a yo-yo at home, go ahead and try some of these simple demonstrations.